Now let's look at the enqueuing process in a little bit more detail. So the pseudocode that you see for the enqueuing algorithm is shown in green. And I want to talk through this, but I will say that when you implement Project 7, you'll want to come back and make sure that you understand this pseudocode. So the idea is that we're enqueuing an element into the priority queue, and you see that EL is the element that's being passed into this function. So what we will do is we will add this element at the end of the heap, and we will then heap up. Okay, so heap up, the pseudocode for that is while that element we're heaping up, while it's not in the root and that element is greater than its parent, then swap the element with its parent. We'll walk through an example here, and that should make a little bit more sense. So let's take a look at an enqueuing example. So let's look at this particular heap that we have at A, and let us add. So this is a max heap. You notice that 20 is, so 20 here is greater than both 10 and 16. 10 is greater than 8 and 7. 16 is greater than 13 and 14. 8 is greater than 2 and 5, and 7 is greater than 6. That's greater than and equal to for all of those. So when we insert 15, we will add it at the end, right? And since we don't skip any nodes, otherwise we will lose the structure property, we will add that node at the end. And so the 15 is now here. Now, as we look at our heap, we have now lost the heap order property because 7 is not greater than or equal to both of its children. 15 happens to be greater than 7. So we will begin then by heaping this node up towards the root. It may not make it all the way to the root, but we will look at it, and if this node is greater than its parent, we will make that move. And so that's the comparison that's going on here, which means that we will put the 7 here, we swap these two, and we'll put the 15 here. Okay, so now the 15 is here, and we're continuing to heap. Remember that we will continue to heap either until we are greater than our parent or until we reach the root. And so we then compare the 15 and the 10 down here, and 15 is greater than or equal to 10, so it gets swapped into that position. So 10 and 15 swap places. And we're still heaping up at this point. We will now compare the 15 and the 20. And since 15 is not greater than or equal to 20, that's one of the conditions to terminate the while loop. So the while loop terminates, and we're left with the tree that's at D, which I've actually made the tree at C equal to this tree. But as we look at it, let's put check marks if we meet the heap order property. 20 is greater than both 15 and 16. 15 is greater than both 8 and 10. 16 is greater than or equal to both 13 and 14. 8 is greater than or equal to both 2 and 5. And 10 is greater than or equal to both 6 and 7. I have check marks by all the leaves, the leaves that have children, and therefore we have restored the heap order property. Let's take a look at dequeuing. So in dequeuing, remember, we're removing the highest priority item. So this particular function does not take a parameter. It does not have a parameter at all. We're just dequeuing the highest priority item. And what we do is we remove that item is always at the root. So we remove the root and we replace it with the node that's at the last leaf. More than likely, this will violate the heap order property, and so we will have to heap that particular node down to its appropriate location. Okay, so there is the pseudocode. So what we're going to do is extract the element from the root. That means remove it. We're going to put the element that's in the last leaf. We're going to put that in the root. We're going to remove the last leaf, okay, because we don't want two copies of this in the tree. And then we're going to set P equal to the root and begin this process called a heap down. And that process is while P is not a leaf and P is less than one of its children, again, we're talking max heap here, swap P with the larger child, okay? And so let's take a look at an example of dequeuing. Let's say that we've got the tree at A and we're going to remove 20. Okay, so we will remove this particular node and we will put the last leaf in its place and we will remove this node. Okay, so that tree looks like the tree at B. We've gotten there. Okay, we now have to heap the 6 down. So we're going to do a heap down by comparing the 6 with both of its children and then swapping it with the larger, because this is a max heap. If this was a min heap, we would swap it with the smaller of the 2 children. So 6 is greater than is less than 10 and 6 is less than 15. But of these two, 15 is the greater one. So we will swap the 6 and the 15. And so now the 15 is at the root and the 6 is here. And remember, I'm continuing to heap down the 6. So I'm here at this point. And so I will compare the 6 to both of its children, which are 13 and 14. And 6 happens to be less than at least one of those. I will take the greater child, in this case 14, and I will swap that with 6, giving us this tree. And now we're here, we're still heaping down, but we're at the leaf. Remember, that's one of the conditions to terminate the heap down. We're at the leaf, and so there's no more heaping down to be done. And the tree at C, which I've converted along the way, is exactly the tree at D. And that tree has restored the heap order property. Let's take a look at it. 15 is greater than or equal to both 10 and 14. 10 is greater than or equal to both 8 and 7. 14 is greater than or equal to both 13 and 6. 8 is greater than or equal to both 2 and 5. And none of the other nodes have children, and the heap order property has been restored. We're still a complete binary tree, and therefore we have restored all property.